Today we're going to be talking about comparing two populations. This lecture is courtesy of Dr. Root and covers Chapter 2 of your textbook. Before we move into this topic, I wanted to do a little bit of review from last class. Okay. So our setup was hypothesis testing, and this was on a single population mean, mu, so that Greek letter. The thing that estimates that mean, mu, is the sample average, x bar, and other things that we had to calculate were things like the standard deviation and the sample size. Okay. Using this information, we calculate a test statistic. This test statistic has the form of an estimated value, which is the sample average, and that an estimated value minus a parameter under the null. So that estimated value, it estimates the population mean, and the value that we give the population mean is determined by the null hypothesis, and then we divide by the standard error. Now, if the estimated value is much larger than the mean, then that's evidence that the population mean is not as hypothesized. It's not equal to the null value. It's evidence of an alternative hypothesis that the population mean is different than the specified value. Okay. When we calculate this test statistic, it doesn't just provide us evidence. It allows us to calculate a p-value in a very specific way that I'll go over. The specific distribution that we wind up with is something called a t-distribution. It has degrees of freedom. It has n-1 degrees of freedom. And this t-statistic resembles a normal distribution. Okay, and so what do we do with this test statistic? Well, we calculate it with the data. We compare this test statistic to its theoretical value or distribution, and we use that to calculate a p-value. Okay, because we know that according to theory, we should get a t-distribution. Okay, and that allows us to calculate the p-value using statistical software such as R or Python, which implicitly uses calculus to calculate the area under the curve. Okay, so depending on your alternative hypotheses, you're calculating the area under the curve here if the alternative is of the form less than. And you calculate here the area under the curve, that gives you your p-value. Okay, and we're seeing that, hey, if the p-value is really small, then that's inconsistent with the null hypothesis. Same thing in this scenario, only that evidence in favor of the alternative is if we have a large value instead of a small value here. But the alternative here is that it's greater than some value. And then the third form of the alternative for a single population mean is that it's not equal to. So here it could be too big or it could be too small. You have to calculate the area in each of these two values to obtain your p-value. So when you obtain your p-value, you could get a p-value that's like 10%, and I like to emphasize that 10% isn't all that rare. It happens like 1 out of 10 times if your null hypothesis is true. You could be unlucky, and you could be one of those 10 times. Okay? So generally a p-value is kind of considered suggestive, but generally inconclusive when it's around 10%. When it gets closer to 5%, we kind of think it's suggestive. When it's less than 5%, okay, that's starting to get more rare, right? But it's still not impossible. So kind of more of a moderate amount of evidence as your p-value edges towards 1% or 1 in 100, and very convincing when it's less than 1%. Okay? I'm showing you this slide because I want you to think of p-value as more of a spectrum. Okay? The traditional p-value testing methodology doesn't leave much for interpretation or thinking about your data. So for example, if you had a significance level of 5%, but your p-value was 0.51 or 0.55, well, that's really close to the cutoff, but technically it's greater than the cutoff, so you'd have to fail to reject it. So, you know, there's some amount of deviation that indicates that a p-value is more of a spectrum rather than a hard cutoff. People really like the hard cutoffs for making decisions because it's easy, but in real life, how do you come up with that cutoff and who gives you that cutoff? That's important to think about. If that cutoff is given to you by your boss, that's great. Hopefully your boss really understands statistics though, and that they're not just making up an arbitrary p-value or decision. So I think it's really important to think about your p-value and think about your data. So moving forward, when you provide your written reports, I'm going to be grading you on using your p-value instead of saying rejecting the null hypothesis at this level of significance. I'd like to see some wording and description that says it's suggestive, maybe it's inconclusive, it's suggestive, but I'm going to conclude this anyway because I believe this about the data. So there's more of a debate about what your data is saying. Okay. There's a moderate evidence. I'd like to see some of that. Or, you know, it's convincing. And yes, this wording is a little bit arbitrary in what various people think is convincing versus moderate versus suggestive. So for some fields, you know, what someone considers convincing might not be convincing in another field. So for example, the cutoff in one field of study could be 5%, but in another it's 1%. Okay, so these things are relative, what people consider to be convincing, and a lot of it has to do with the domain. Okay. But just as a reminder, please start using this terminology in your written reports. Okay. Now, returning to our area of application with the schizophrenia data, there were 15 sets of identical twins with and without schizophrenia in the US and Canada, and they measured the hippocampus volume in the brain. Okay. So there's a question here. What can we conclude? So there's two things we can ask about inference. What can we conclude in terms of the p-value? What can we conclude concerning the sampling design? So because we have identical twins and a match paired experiment, we have a data set that is likely to account for any confounding variables because of the matching. Okay, so the inference here is very strong. Probably want to be a little bit careful about what population we're making inferences about. So probably want to restrict this to US and Canada. If you're the researchers, you probably want to try and generalize this to any individuals with and without schizophrenia, and there'd be a set of arguments and things to discuss that have more to do with genetics, and that's a little bit beyond my realm, but we can safely make this our scope of inference or a population to the set of identical twins. It probably applies to a larger demographic. And one reason why I'd be okay with that is because of the matched pair design. So in the schizophrenia data, is group 1 independent of group 2? So there's an answer there, no, so I gave it away a little bit, or I should say Dr. Root did. And the reason why is group 1 is the schizophrenic side, group 2 is the non-schizophrenic. Group 1 likely affects group 2 because somewhere in group 1 is a twin and somewhere in group 2 is their sibling. Likely the genetics or other factors such as nutrition and income affect the other twin in group B. So it's highly believed that group 1 is correlated or has an effect on the other group because of the fact that they're identical twins. So in order to eliminate this dependence, we have to do a paired t-test and take the difference family-wise, that is with the affected versus unaffected twin. And those difference data is now independent. The difference of me with my twin, if I had one, would be unlikely to affect the difference of someone else with their twin. And that makes sense. Okay? So because of this, it's really important to take the difference and use a one sample test. Okay. So in the schizophrenia data, when we're applying the one sample test, we need to check the assumptions. So one of the assumptions is normality. The typical standard is to have a graphical display. So here we have a box plot. You could do a histogram. The most common is a QQ plot. Okay, and that's really what should be here is the QQ plot. Okay, but a box plot, a histogram, they're also acceptable. So based on this box plot, it looks pretty symmetric, fairly normal. The only thing that tells you it's not normal is the fact that the median isn't in the middle. So the question is, could the median not be in the middle due to random variation in the normal distribution? So it's not immediately obvious that it is or is not. So that's kind of evidence that maybe you wouldn't reject your null because there's not overwhelming evidence that it's not normal. It does seem a bit far off from the middle. So the second thing that you'll do is you'll run a numerical test when it's possible. And here, for normality, it is possible. There's a test for distribution. So it's called the Shapiro-Wilks normality test. The null hypothesis is that the data is normally distributed versus the alternative that it's not normally distributed. When you run this, you'll get a p-value of 0.11, and if we go back up here, it's inconclusive that the data is not normal. So we're going to go ahead and conclude that our data is normal, and it turns out that the difference in this median not being in the middle is due to random chance. Okay. When we run our t-test on this difference data, it produces this t-statistic right here, this 3.22, and that is calculated by calculating this statistic, x bar minus 0 divided by the sample standard deviation divided by root of 15. Okay, so that's that t-statistic. There's 14 degrees of freedom, and it gives me a p-value of 0.006. This is less than 1%, so it means that there's less than a 1% chance of observing this difference in the data. If the null hypothesis is true, I conclude that this is convincing evidence. The data is not consistent with the null hypothesis, and the difference is not due to random chance. So I conclude that the mean brain size of schizophrenic individuals or twins is different than non-schizophrenic. The 95% confidence interval indicates that this difference could be as small as 0.066 cubic centimeters or as large as 0.33 cubic centimeter. The average difference is going to be about 0.19 or 0.2 if you want to round. Okay, when we run these tests, we're going to get various different errors we could make. Okay, so one error is called a type 1 error, and that means that we reject the null hypothesis when the null is actually a true value. Another form of error is called a type 2 error, meaning that we fail to reject the null hypothesis when the alternative is true. A type 2 error would mean that the test cannot differentiate between the null and the alternative hypothesis. So the opposite of that is called power, okay? And power means that we're in the scenario here with this bottom right, that we are able to reject the null when the alternative is true. And high power is a good thing. It means that you're able to correctly reject a false null hypothesis. And the probability that we do that, well, that gives us power, and more power is better, okay? Now, when we do our statistical methodology, paired tests have a higher power because of this pairing. It makes it easier to calculate the variance, okay? So as we're going to see, the variance can be a bit more difficult when we're not able to pair our data. Okay, we also reported a confidence interval, so we're going to discuss that now. So if we want to calculate a confidence interval, it comes from this formula here. We would use this formula in this distribution to derive this formula. Okay. The confidence interval has this form, which is an estimated value plus or minus. Instead of standard error, I'm going to call it a margin of error. Okay, a margin of error is everything after the plus or minus from the sample mean. Okay, so common confidence interval forms are 90%, 95, 99, but really you can do anything in between 90 and 100. That's generally acceptable. I know a statistician that likes to do 89% just to piss people off, but you know, I recommend doing the standard thing. Okay. I don't really recommend going below 90% just because it's a tad less certain. So that would be my one piece of advice. Okay. So what this confidence interval tells you is it tells you 90% of the data is in this interval between the two red regions, and that is a confidence interval on the difference here, okay? So when you have a 90% confidence interval, that means alpha is 10%, so there's a 5% chance alpha over 2, 10% over 2, or alpha over 2 is 5%. There's 5% in each tail, so there's a 5% chance that it's bigger than the upper value of your confidence interval, and a 5% chance that it's less than the lower value of your confidence interval. Okay, so that gives you important pieces of information as to like how rare those values could be that you're seeing. Okay, and now we're going to do the same thing, but we're going to do two populations. So when we're comparing two populations, different setting, we want to compare population 1 to population 2. That's our null hypothesis, is always a statement of equality. The alternative is that one is bigger than the other, or that the two values are not equal. Okay? When we're comparing two populations, we need a test statistic. It's ideal that they have the same variance because then we can pool the standard deviation and get a better estimate of the standard deviation. And in that scenario that you can pool, that the two populations have the same standard deviation, this is how you would pool it. This is the formula. Now you'd use this, and you need the standard deviation to calculate a test statistic. So you calculate this test statistic, okay? And the denominator here is the standard error, The numerator is evidence in favor of the null or the alternative. Let me go to the next slide, but it's also important to note, in this scenario, the degrees of freedom is sample size 1 plus sample size 2 minus 2. Okay. It didn't go here, so let me talk about this slide. So under the null hypothesis, mean 1 is equal to mean 2, so that means that this term here, mu1 minus mu2 in the numerator, goes away. And evidence in favor of the alternative hypothesis, that population mean 1 is bigger than population mean 2, would be a large positive value of this t-statistic, because ideally the sample average of population 1 would be larger, much larger, than the sample mean of population 2. So we're looking for large t-values here. And this t-statistic provides evidence in favor of the null or the alternative, and then we calculate a p-value, just as we did before, to really assess how rare that is, how consistent our data is with our null hypothesis. Okay, now just like before, when we have two populations, it's really useful to calculate the confidence interval on the difference. So that's given by this formula, the difference in the two sample means plus or minus the standard error, so the estimated difference plus or minus a margin of error, and it has these degree of freedoms. Notice that there are some assumptions or requirements for this test, just like there was with the difference data. So we're going to talk about, in this example, Darwin's finch data. And we want to know if pooling the variance is the most powerful test. Sometimes it's not warranted, but then you'd be fooling yourself in thinking that you're applying the appropriate statistical test and making the correct decisions. Okay, so to know if you can pool the variance, there's a test for it. Okay. So you can assess visually with a box plot or a histogram. Then there's a test, it's a statistical test, so you can do a visual analysis, and then you can do a p-value assessment. And this is called Levine's test. So in Levine's test, the null hypothesis is the variance the two populations are equal. The alternative is the variance the two populations are not equal. If, in fact, the Levine's test says, hey, the variances are different, well, you shouldn't pool it. Like, you shouldn't say the variances are equal when they aren't. So we need a different statistical methodology. When the two populations have a different variance, this is the test statistic you'd calculate. And again, under the null, it reduces to just this, because under the null, they're equal. Okay. The degrees of freedom is given by this messy formula. You can see page 98 of your textbook, okay? But I'm not going to ask you to derive it. And the degrees of freedom can be calculated for you using statistical software. Now, if you want the most powerful test, you need to use the correct statistical test. So use the pooled variance when it's appropriate. Use the non-pooled variance when it's appropriate. Okay? But notice the degrees of freedom is always higher if you had to pool, so this is the typo, if you had not pooled the variances, which means your test is less powerful when you can't pool the data. Okay? So you have a higher probability of failing to reject the null hypothesis if you use the pooled test and if the assumptions are met. Okay. So key point is that it's really important to check the assumptions of your test, of your data, and then to apply the correct statistical methodology. So assumptions of your test is that the data is obtained from a random sample of the population. or is representative of the population. And I put that or there to give you an out in case your data isn't random, because a lot of data that's collected is not random. It's less than ideal, but it should be, okay? And a lot of people try and skirt around this by saying, well, I think it's representative of my population. Well, then you're good to go. But are they really doing a good faith effort? Probably not. Okay, so you should be cautious in that scenario. The sample data is independent of each population, so what happens in group 1 should not affect group 2. Okay, it should also be independent within the group, so one observation should not affect the other. The data should be normally distributed, or the sample size should be bigger than 30. Okay, if the data is less than 30, you need to inspect the data with a histogram or a box plot, or determine if the data is roughly normal. And then lastly, you could use a Shapiro test for normality. Okay, so when you assess your assumptions, for visual assessment, box plots can assess normality and equal variance. Histograms can assess normality and equal variance. QQ plots only assess normality, but they're the best at assessing normality. Then the Shapiro test is a numerical test. It produces a p-value, so that's what I mean by numerical. It's a test of hypotheses of normality. Levine's test provides a numerical measure, and it produces a p-value by testing the hypothesis that the variance of the two populations are equal. Then independence, that has to be assessed by the sampling method or knowledge about the data. So that's perhaps the most, the one that is the most subjective is independence. Okay, thank you very much.